Hey, welcome back. This is 8.5, continuing on with integrals, integration. So some people would say that integration is an art. If you go on YouTube, there's kind of like this integration versus differentiation showdown. Integration versus differentiation, which you may or may not want to. Oh, they have integration bees, like spelling bees. But they had this one video. Here it is, the derivative versus the integral, the final smackdown. Which you may or may not be interested in watching. I guess it's kind of funny. Maybe it's not MIT, it's Williams College, but it's a MAA is like a math association, so if you become like a math teacher or a professor or something, you want to be part of. So honestly, I'm not part of them, so I'm not going to give them any props. But yeah, so they go through and kind of go back and forth about which is better, and they give arguments, which is better, the derivative or the integral, that sort of thing. Okay, great. So that's a little slice of life from the outside world. Let's get back to our work, though, unfortunately. 8.5, partial fraction decomposition. How does this work? Basically, what are you dealing with? You're taking one fraction and turning it into two. Okay, so the deal is we are used to taking two fractions and turning it into one. So making one fraction from 2, right? So hopefully you recall this process in algebra. Maybe you'd have 2 over x minus 3 minus 4 all over x plus 4 or something of that nature. So to add them together, you have to find a common denominator. For the first guy, you're going to have to multiply top and bottom by x plus 4. The second guy, you're going to have to multiply top and bottom by x minus 3. And then you can combine the numerators over the common denominator. So the first numerator, when I distribute, will give me 2x plus 8. The second numerator will be 4x minus 12. Distributing the negative, you get negative 4x plus 12 over x plus 4 times x minus 3. 2x minus 4x is minus 2x plus 8 plus 12 is 20. All over x plus 4 times x minus 3. And then you always hope you can simplify. I don't think we'll be able to simplify this. Now we want to go in the other direction. So now we'll have something like 15x all over x minus 3 times x plus 1. You know, something of that form. Just look at the top example, you can kind of guesstimate kind of a first step. Notice to take this fraction at the end and kind of split it into two new fractions. Each fraction has one of the factors in the denominator, and that's going to be kind of the way we set these up in the beginning. So what we'll do is, if you have two factors in the denominator, you can turn that into two fractions, and then just have some unknowns in the numerator, and then somehow we'll have to figure out how to figure out what is A and what is B, right? Okay, so that's the kind of the spiel. There's 4 different kinds of setups for these based on these denominators, and we have to go through all 4 types. And then there's 2 methods for solving for the numerators, and we'll have to go through those as well. Okay. So maybe the last question is kind of why? Why the heck would I want to do this? And look at the original integral up there versus the simplified. So if I had started with negative 2x plus 20 all over x plus 4 times x minus 3, and let's say we wanted to integrate that thing, compare it then with its kind of decomposed form, right? So the decomposed form would be 2 all over, and then 2 all over minus 4 all over, and then the denominator is x minus 3 have here x plus 4. So I don't know how to do this first integral, is kind of the point. I don't know how. But I do know how to do the second integral, right? So the second integral is just 2 ln absolute value of x minus 3 minus 4 ln absolute value of x plus 4 plus c, and I'm done, right? So that's the reason. That's why we want to do the decomposition. And so you have some motivation, right? So let's dive right in and see if we can kind of figure out how this works. And the way I'll go is I'll show you the setups, and then we'll work on determining the A and the B's, so to speak. Okay. So 2, this is setting up partial fraction decomposition, which I'm just calling partial PFD. Okay, so first off, the first thing to note is kind of this factoid. If the whoops, I just butchered that F for you. Sorry about that. If the degree of the numerator is greater than or equal to the degree of the denominator, you have to do long division. Okay. Doing a partial fraction decomposition will not work in those cases, so you need to first simplify them, and hopefully we've kind of beaten that to death. Okay, so anyways, setting them up, right? So the first kind of setup is what we started with, and basically we have linear, what are called linear factors. Okay, so you would want to factor the denominator if it's not already factored, and then the form we're looking at is kind of the setup. Let's not even say setup because I already said setup above. Let's if I can get my eraser to work. There we go. The first form are linear factors. Okay. From pre-calculus, you may have learned that any polynomial can be factored into linear factors, which look like this. And quadratic, irreducible quadratic factors. And of course, later you learned if you include the complex numbers, you can always go into linear factors. But if you're not including complex numbers, sometimes you're left with these kind of expressions like x squared plus bx plus some other c value, right? So any polynomial you can supposedly factor into terms like that. So these guys right here are the linear factors, and that's what we're dealing with in the beginning. So all we see are linear factors. And linear factors, so example, they look like things like 3x minus 2, x minus 3, 3 minus x, just plain old x is a linear factor. Any of those guys. Okay, so let's take a look at some sort of examples of setting these up. So let's say our integrand is 8x minus 1 all over x minus 2 times x plus 3. Okay, so what we're going to do is just, at first set it up into two fractions, and each fraction gets one of the factors. So we'll put the x minus 2 in the first one, don't need parentheses, and the x plus 3 in the second one. And the numerators, I put a and then b. Okay. Let's look at another x squared minus 4x minus 12. Okay, this denominator is, right now it's a quadratic factor, but we can reduce it into linear factors. Okay, so I'll have x plus 34 all over, looks like x minus 6, and then x plus 2. And again, then we have two factors, so we need two fractions, and we'll have x minus 6 and x plus 2. Put a in the first one, a b in the second one. If you think we had three factors, you would just, then you would have a third fraction. So let's look at maybe one like that. So 4x squared minus, right now the numerator doesn't matter. The numerator will be important later when we solve for the constants. Okay, I just want to get all the different setups out of the way. before we go there. Okay, so again, the denominator here is not factored. So I can factor out an x, and then I'll have x, and it looks like -5, and then +1. Okay. So this time we have 3 linear factors, and again, that just by itself, x is a linear factor. It's like x plus 0. So you'll have 3 fractions. One of the fractions will just be x, and then you'll have x minus 5 and another one. And it doesn't matter what order you put them in. Addition is what they call commutative, so 3 plus 2 is the same as 2 plus 3. Okay, so you could put them in, you could put x minus 5 in the first denominator, and then x in the second, and then x plus 1 in the third. That's fine too. In the numerators, you're just putting sort of constants that we'll solve for later. Okay, so there's that. That's the first case, linear factors. The second case is when you have repeated linear factors. So maybe going up and looking at my example P of x, maybe you have then x minus 3 times x minus 3. And that would be considered a repeated factor. And that requires a different setup. Okay, so we call these repeated linear factors. And let's take a look. So these aren't problems in the book or anything. These are just made up examples, probably at one time based on the book, but not anymore. Okay. So the way this one pans out is you need a fraction for every factor. Okay. So in this case, we have 3 factors of x minus 1. So I need 1, 2, 3 fractions for each factor. Okay, in the first fraction, you just put x minus 1. In the second fraction, you put x minus 1 squared. In the third fraction, you put x minus 1 cubed. Okay, if it was x minus 1 to the fourth, you would just add another fraction, then put x minus 1 to the fourth in the denominator. And the tops, it's the same game. You just put a, b, c, d, e, f, whatever. Okay, so it's pretty simple. Let's look at another one. That's kind of a mix-mashed hodgepodge of the 2 different types. So here we have x squared times x minus 3 times x minus 1 squared. Okay. So I have 2 repeated factors of x, so that needs 2 fractions. 1 x minus 3, so just 1 fraction there, and then 2 more fractions for x minus 1 squared. So I should have 1, 2, 3, 4, 5 fractions. And you hope you don't see them like this because it becomes a lot of work, right? So first I go x and then x squared, and then I need 1 fraction for the x minus 3, and then I need x minus 1, and then x minus 1 squared. Okay. Up top I just go a, b, c, d, e. Okay, so kind of a nightmare. The next types are called irreducible quadratics. So this thing right here is a quadratic factor. In the complex numbers, you can always factor quadratics, but things like x squared plus 5, right? It will only factor in the complex numbers. It would be like x minus root 5i, and then x plus root 5i. Right, so in the real numbers, it's called irreducible. But in the complex numbers, it is reducible. But we call it irreducible quadratic, and we're not going to be playing with the complex numbers in our class. Okay, it takes complex variables class to do that. And some engineering classes are like that. But so here we'll start with just single factors, and then the fourth type will be the repeated irreducible quadratics. Okay, and then that's it. Okay, so part C, irreducible quadratics, and these will be usually in the book they'll end up looking like x squared plus 5, but they can also have other forms. I don't have a good example here, but something like x squared plus x plus 1, right? That thing's not going to have factorization in the real numbers. You would end up with like a radical in your discriminant, right? So plus or minus square root. The factors would be x equals. The zeros would be that, and then you would use that to get your factors. So 1 plus or minus the square root of b squared minus 4 times a times c. And you can see it's imaginary all over 2. So irreducible. And we're not going to worry about square roots either. Those aren't going to be coming up. So if you did have something like x squared minus 5, that's technically not irreducible in the real numbers because you just do square root 5 for your factors. But that's not going to come up in our problems here. Okay. So let's look at some examples of these. Just doing the setups. Let's see if I can find some. Forget what number I put myself on, number 6. And here we go, x squared plus x minus 6 all over x squared plus 1 times x minus 1. Okay, so I need a fraction for x minus 1. And that just works like we trained you to do it above. Okay, so you need a all over x minus 1. Then what you're going to do for the irreducible quadratic factor, which is this guy here, x squared plus 1, you're going to give it its own denominator, its own fraction. So just like before. But now in the numerator, that's the part that's different. So in the numerator, before you were just putting constants. Now you're actually going to put another linear factor. Okay, so it's almost like you go down 1 degree for the polynomial. If it's quadratic, then in the numerator you go first degree, which is a linear factor. So let's look at another example. And we have x squared minus 1 all over x cubed plus x. Okay, this thing needs factored first. So I have x squared minus 1 all over x times x squared plus 1. Okay, and then I have 1 linear, the x, and then plus the 1 quadratic. So that's x squared plus 1. And the numerator, you put bx plus c. Okay. Let's then move on to the repeated irreducibles. And what's going to happen there is you're just going to do it like you did the repeated linears, right? If you have like x squared plus 1 to the 5th, you're going to need 5 fractions. The first fraction, its denominator, will be x squared plus 1. And the next fraction will be x squared plus 1 squared. Then the next x squared plus 1 cubed. Then the next x squared plus 1 to the 4th. Then the next x squared plus 1 to the 5th. Okay. So let's show you some examples. D, repeated, irreducible, quadratics. Right. So let's look at number 8. And where are you? Okay, I found it. 8x cubed plus 13x all over x squared plus 2 squared. Okay, so this time x squared plus 2 is irreducible, and then it's squared, so I need 2 fractions, one for the x squared plus 2, then one for the x squared plus 2 squared. Then in the first numerator, I'm putting ax plus b, and then you just carry on cx plus d, so you don't have to change the numerator any. Just like with the linear factors that were repeated, I still just go a, b, c, right? So you're still just putting some linear factor, cx plus d, ex plus f, etc. So let's look at one that's hardcore, a hardcore example that kind of combines everything above. So here we have x cubed times 2x plus 7 times x squared plus 5 squared times x squared plus 1. Okay, so how many fractions are we looking at? So 1, 2, 3 from that guy, 4, 5, 6, 7. Okay, so x squared, x cubed, 2x plus 7, x squared plus 5, x squared plus 5 squared, x squared plus 1. And then up top you go a, b, c, d, e, x plus f, g, x, e, f, g, h, I, x, I, j. Okay? And you hope you don't really ever see one of those on a test. Okay. So that's how you set it up, all right? Great. Now let's take a look at actually finding those numerators. This is section 3, solving for numerators. And there's two methods as promised. The first is called equating coefficients. And this method becomes important later in differential equations. You'll use this method on other things. And actually, you keep doing partial fractions a lot through differential equations. These kind of integrals pop up a lot. So anyways, equating coefficients, this method is a surefire method. It's always going to work. The other method is quicker, but it don't always work. So just be aware. So anyways, how does this work? Note the following fact, which you may or may not be familiar with. Note following sort of idea. If we have a plus b x, let me write it in the other way around. So I'm going to put some numbers on one side. So I'm going to go 3x squared plus 2x minus 1. And on the other side, I'm going to put a plus b x plus c minus d, oops, x squared, and then this got to be x, and then plus, I don't know, we'll say c. Okay. Okay, if you have an equation that looks like this, you can equate the coefficients, and it is exactly what you think it is. You just take a plus b and equate that to the coefficient over here on it. So a plus b is a coefficient on x squared here, so that must be equal to 3. Right? And then c minus d is the coefficient on x, so that must be equal to 2. And then finally, the constant is c, so c must equal -1. And then you could solve that system of equations. So again, what are we dealing with? I have a plus b equals 3, and then you'll have c minus d equals 2, and then we have c equals -1. And then hopefully, I don't think in this case you can, but hopefully you can solve these equations for a, b, c, and d. And that'll give you the method of equating coefficients. Okay, okay, so that's the idea. Let's actually go and try one of these characters then on this example from the book. So I have 5 all over x squared plus 3x minus 4. Okay. So the first thing I'm going to do is factor the denominator if possible. So I have x, it looks like it is, right? So x plus 4, x minus 1. Okay. So the partial fraction decomposition setup is going to be a all over x plus 4 plus b all over x minus 1. Okay. And this is kind of the starting equation that I need. Okay. So the first step once I have this equation is to multiply both sides to get rid of all the denominators. Okay. So I'm just going to rewrite it. And then I multiply this side by the x plus 4 times x minus 1. And I multiply this side times x plus 4 times x minus 1. Excuse me. And on the left, both denominator and that factor, the factors, excuse me, I'm multiplying by are eliminated. On the right, I have to distribute. So on the first distribution, the x plus 4s will cancel, and I have a times x minus 1. And the second distribution, the x minus 1s will cancel, I have b times x plus 4. Okay. And now I'm going to kind of, oh crud, this isn't the example I wanted to show, is it? Oh well. Well, okay, so it's not going to be as obvious. I'll do another example here in a second, but Okay, so now what I'm going to do is distribute the a. So I get ax minus a plus bx plus 4b. And then you need to quote-unquote equate the coefficients. The issue is on the left, I don't see an x term, but you can kind of cheat and say 0x. Okay. So 0x equals ax plus, I'm going to group the like terms together, minus a plus 4b. You could factor out the x from the ax plus bx, and you kind of see, okay, a plus b is the coefficient on x. And then I can equate that to 0. And then the constant part is just the negative a plus 4b. Okay. So again, you're equating coefficients. So a plus b is the same as 0. So I could write that out. A plus b is equal to 0. And then the constant part, negative a plus 4b, that must be just 5. Okay, so I'll have negative a plus 4b equal to 5. And then you have a system of equations and two unknowns. You could solve that system. So over here, I could solve solve b for, or whatever. Move the b to the negative b here, and then plug that in over here. So I have negative b plus 4b is equal to 5. So that'll be 5b is equal to 5, and then b equals 1. And then plug that back in over here. So a will equal negative 1. And finally, then you have your fraction decomposition. So ultimately, you have 5 all over x squared plus 3x minus 4 equals negative 1 all over x plus 4 plus the b value, which I thought was 1, all over x minus 1. Right? Yeah. Make sure you get the a with the right factor. So the a needs to be with x plus 4, and it is. And then b needs to be with the x minus 1, and it is. Okay, let's do the other method now. So now we move on to method 2. And method 2 works in the beginning the same way. Okay, so that was method 1. This is method 2. And I just call this like a substitution method. Doesn't always work though. So just one thing to keep in mind. It seems like it works if you use imaginary numbers. I've never really done it though, so I can't, advocate that method. But this method is quick and it's doable in your head. If you're doing PFDs all day long, you can get this method down in your head. Okay. So in some differential equations classes, this method is quicker, but it's up to you. You can always do the equating coefficients method. It's just a little longer. So anyways, it kind of starts the same way, right? So we had this fraction, we factored it, we have 5 all over x plus 4 times x minus 1, and that equals a all over x plus 4 plus b all over x minus 1. So the first thing we did was multiply both sides. That's what we do here as well. X plus 4 times x minus 1, x plus 4 times x minus 1. These will cancel. You get 5 equals a times x minus 1 plus b times x plus 4. Okay, so what you're going to do is substitute in values for x that get rid of either a or b. So note, if you let x equal 1, the a value is going to go away and you're going to get an equation in terms of b. Okay, so watch. You get 5 equals a times 1 minus 1 plus b times 1 plus 4. Okay. So 5 will equal a times 0, which is 0, and then b times 5, which is 5b. And so you get b is 1, just like we got above. And then let x be negative 4, right? So you get 5 equals a times negative 4 minus 1 is negative 5, and then plus 0. Divide both sides by negative 5, and a is negative 1. okay, which is exactly what we got above. A is -1, B is 1. Okay. It's a lot quicker. It's just like I said, it doesn't always work. And the equating coefficients method, you'll use that again. So anyways, let's dive in here and look at maybe a harder one. And 1 or 2, and then see how that goes. Okay, so section 3 with integration now. Okay, so let's look at this example. Integral of x squared plus 12x plus 12 all over x cubed minus 4x dx. Okay. So first thing you want to do is just get the partial fraction decomposition out of the way. So I'm going to borrow the guts of the integral. I'm going to factor the denominator. I can pull out an x. So this, just so I don't have to rewrite things a million times over. This will be x times x squared minus 4. And then x squared minus 4 is the same as x minus 2 times x plus 2. Okay, so fully factored, the denominator is x times x minus 2 times x plus 2. Okay. Okay, and then my setup, I need 3 fractions. One for the x minus 2, and one for the x plus 2. And in the numerators, I'm going a, b, c. Okay, I'm going to use the equating coefficient method here. And in order to pull it off, I have to multiply both sides by by x. I'm really going to have to smush this in. I apologize. X minus 2 and then x plus 2. Well, no, we can use the magic of the whiteboard to just move this over a little bit. Huh. Ain't that special. All right. Okay, so I'm going to multiply both sides by x times x minus 2 times x plus 2. So used to writing on a whiteboard that I forget I have the ability to do things like that. Okay, so on the left, this stuff will go away. Just be left with x squared plus 12x plus 12. On the right, you have to distribute. So we'll have a times x minus 2 times x plus 2 plus b times x plus 2 plus c times x minus 2. Okay, then I need to FOIL and factor all this junk, multiply it all out, and then start gathering all the like terms and equating coefficients. So this will be x squared minus 2x plus 2x is 0. Minus 4, distribute this character, dx squared plus 2dx, distribute this character, plus cx squared minus 2cx. And it always, the order of letters there, it always goes number, capital letter, and then your variable. So the variables always last. So order of importance, or I don't know. So you can see I'm not writing x2b, right? Just like you don't write x2, you write 2x. Okay, so there's an order here. You put the constant up front, then the variable. Sorry, the constant, then the letter, then the variable. Okay, anyways. X squared plus 12x plus 12. Distributing, I have 8x squared. And I'm going to move the bx over. Bx squared plus cx squared plus 2bx minus 2cx. And then there was a minus 4a from this first distribution that I kind of pushed to the back. Okay, let's make sure I got them all. Got that, got that. Got this, and I got those two. All right. Now you can factor out the x squared from the first 3 terms and kind of see, all right, I can see what the coefficient is on the x squared. Then you could factor out the x from the next 2 terms, and then minus 4a. Okay. So now equating coefficients, over here the x squared is 1. Okay, so a plus b plus c is equal to 1. The coefficient on x is 12, so I'll have 2b minus 2c equals 12. And then the constant term, negative 4a, just equals 12. Okay, so first I can solve for a. That will be negative 3. And then you want to reduce the number of variables over in this first equation, so I can go and plug in negative 3 for a in the first equation. Like this. So I have negative 3 plus b plus c equals 1. Then I can solve for c, I guess. So c will equal 1 plus 3 is 4 minus b. And then I can plug that in here. So I have 2b minus 2 times c, which is now 4 minus b, equals 12. And then I'll have 2b minus 8 plus 2b equals 12. And then 4b equals 20, and so b is 5. And then finally I could plug that character into here, and I get c equals 4 minus 5, which is negative 1. Okay, so I have my a, b, and c terms, and now I can proceed with my integral. So this is all just scratch work, everything I just did. And now it allows me to rewrite my integral as a over x, the heck was a, negative 3 over x plus b over x minus 2, and then plus c all over x plus 2 dx. Let's make sure I got them in the right places. A with x, b with x minus 2, a with x, b with x minus 2. Yeah, okay. And then each one of those is just a natural log, right? So you get negative 3 ln absolute value x plus 5 ln absolute value x minus 2 minus 1 ln absolute value of x plus 2, and then plus c. And that's it. Okay. Let's do one more. We haven't done a quadratic factor yet, so let's do one of those. This used to be 25. I doubt it is anymore. Just call it an example. Okay. So evaluate from 1 to 2 the integral x plus 1 all over x times x squared plus 1 dx. Okay. So this time I will do coefficient method again. I'm going to do that method again. X times x squared plus 1. Okay, so I have two factors. One is linear, one is irreducible quadratic. So I have one fraction for the linear, one for the irreducible, and this will be a, this will be bx plus c. Okay. Okay. So I want to multiply to get rid of the denominators. As usual, I didn't leave myself enough room to do that, so I'm going to move this over here. Okay. So I got x times x squared plus 1, x times x squared plus 1. So left with x plus 1 there. On the other side, I have a times x squared plus 1 plus bx plus c times x. So I have x plus 1 equals ax squared plus a plus bx squared plus cx. There's no x squares on the left, so I'll just make up 0 x squares for my equating coefficients. I'll have a plus then b x squares plus c x's plus a. Okay. Then I can equate coefficients, so I'll have a plus b must be 0. Right? A plus b is 0. Then you'll have c is 1. Right? Don't see anything there, there's a 1. So c is 1. And then finally a is 1. Okay. Okay, so what you really need to figure out is b. Oops, I should have made that b is negative a, right? And so b is negative 1, and that's our partial fraction decomposition. So let's get it. Our integral will now be 1 all over x plus negative x plus 1, bx plus c. all over x squared plus 1, and then dx it. Don't forget we have to evaluate from 1 to 2. Okay, so the first integral is the first part is a natural log. The second part, I'm going to have to split it. So we'll end up having 1 over x dx minus the integral of x all over x squared plus 1 dx, and then plus the integral of 1 all over x squared plus 1 dx. So all I did there was to separate this integral, this fraction, into two fractions, so a reverse decomposition. And then I ended up where I am now. So, okay. The second integral is going to require a u sub. I should do the work below here. U is x squared plus 1. And then du is 2x dx. And then dx is du over 2x. Okay. So anyways, what do we have? 1 over x dx minus the integral of x over u times du over 2x, and then plus the integral of 1 over x squared plus 1, which is just an arctan integral. So this will be integral of 1 over x minus factor out 1/2, cancel out the x's, du over u plus the integral of 1 over x squared plus 1 dx. This will be ln absolute value of x minus 1/2 ln absolute value of u plus 1 all over a is 1 in this case, tan inverse of u, which is x over a, which again is 1. And then we have to evaluate. I need the back sub before I can evaluate, though. U is x squared plus 1. So ln absolute value of x minus 1/2 ln absolute value of x squared plus 1 plus tan inverse of x. Evaluated, I think it was 1 to 2. Okay. Plugging in 2, I get ln 2 minus 1/2 ln of 2 squared is 4 plus 1 is 5 plus tan inverse of 2, and then subtract away, minus ln of 1 minus 1/2 ln of 2 plus tan inverse of 1. Okay, so I have ln of 2 minus 1/2 ln 5. This is a big 0. This thing is pi over 4. And so, what do we get? Plus tan inverse of 2 minus 1/2 ln of 2 plus pi over 4. Then you have, 1 ln 2 minus 1/2 ln 2 is 1/2 ln 2 minus 1/2 ln 5 plus tan inverse 2 plus pi over 4. And that's a pretty solid answer right there. You can combine these two using rules of logs. It'll end up being ln of the square root of 2 over 5 and then plus tan inverse of 2 plus pi over 4. Right? You can take a look at that. It'll be 1/2 ln 2 minus ln 5, which is 1/2 ln of 2 over 5, which is equal to ln of 2 over 5 to the 1/2, power rule. And then, of course, that's just ln of the square root of 2 over 5. Maybe you want to rationalize that? No. Leave it at that. Let's get you a quiz question here. Decided to neglect the quiz question. So, we'll just do a partial fraction decomposition. Okay, so for the quiz, the video quiz question today, set up a partial fraction decomposition and all I want you to do is like we did in the beginning here, like with number 9. You don't have to solve for the coefficients. All I want you to do is set it up. Okay. So it's going to be one of these nightmare scenarios. 2x squared minus 2 plus 1, 2x plus 1, all over x squared plus 1 cubed times 2x minus 5 squared times, let's put an x in there, and then maybe another x squared plus 5. Okay. So just set it up. You don't have to solve it, and that will be your quiz problem for section 8.5. So this is starting now into the next video homework assignment. Let me mark it down in my notes. Okay, so you should have 1, 2, 3, 4, 5, 6, 7 fractions, right? 3, 4, 5, 6, 7 fractions. Okay, we'll see you next time.